Hi, my name is John Josephakis, Vice President of HPC Sales at NVIDIA. Welcome to ISC 21 and the NVIDIA Special Address. It's been an exciting year for us with many announcements, from the A100 GPU to the NDR networking technology, all the way to our first ARM Grace CPU. But that's not it. We also announced a lot of software frameworks which enable scientists to use our hardware platforms to accomplish their goals. We had a number of wins on the Euro HPC program, and we also announced our CSCS ARM-powered Grace CPU system in Switzerland with CSCS. Data sciences in AI have had a big impact to advance modeling and simulation. Accelerated computing is driving exponential growth in many areas, like manufacturing and drug discovery. The need to solve large problems has driven people to larger systems using AI and accelerated computing. But for more on that, I'll hand it over to Mark Hamilton, our VP of Solution Architectures and Engineering. Mark, take it from here.
Thanks, John, and welcome again, everyone, to our ISC 21 special address. ISC has always been a time for the HPC community to gather and celebrate our successes from the past year. And what a year it's been. When we went into ISC 20 a year ago, the first digital ISC, I'm not sure anyone thought that ISC 21 would still be digital only. Yet here we are. I have to reminisce a little bit and think back to 2 years ago and many other years in Frankfurt. Anyone who's ever been to an ISC in person in Frankfurt and gone to any of the vendor events at the Marriott Hotel will certainly remember that walk. Out the front doors of the convention center, past the lunchroom, across what seemed like a vast and endless parking lot, through the back gates, out to the street corner, wait for the street light, cross the street, cross another street, the tram lines across Hamburger Alley, make sure you're not going to get hit by a train, into a vendor session, maybe the NVIDIA vendor session at the Marriott Hotel. And if you work for NVIDIA, you probably did that walk 5 or 10 times a day, 10 minutes each way. So being digital does have its advantages. So let's go ahead and get started with the show. Before that, a quick reminder. This is live, and for the last 20 minutes, we'll be having a live Q&A. So if you think of any questions as I'm presenting, go ahead and put them in the Q&A window. We have a distinguished panel of AI and HPC experts from NVIDIA that will help me address your questions at the end. For years, we've seen industries transformed by HPC, including NVIDIA. For 20 years, NVIDIA has worked with companies like Industrial Light and Magic using HPC to create amazing scenes of special effects in movies. I know many of you have probably watched The Rise of Skywalker, the epic lightsaber battle on the dying Death Star, as waves from the ocean rolled over the actors over the boat. ILM simulated 135 million gallons of water in filming this scene, which would of course have been impossible to do without NVIDIA GPUs. And today, and since that film, I'm sure many countless young kids have replayed that out on a summer lawn or in their bedroom, dueling away with lightsabers. Probably a few of you adults at the show too. Our own products. NVIDIA isn't just about what we build. NVIDIA is about how we build it. And simulation has become a culture at NVIDIA. Our processors are fully simulated before we ever send the designs off to the fab to be built. We don't press the go button until we're really sure that that processor is going to come out error-free on day one. That leads us to quicker time to market, not having to repeat build cycles in the fab, and higher quality products. And of course, especially over the last year, we've all used the internet more to buy things, to work from home, maybe even to shop and play a little bit. And internet services are today powered by supercomputing. Recommender systems are at the heart of every internet service. And of course, natural language programming. NLP has become the poster child for AI and high performance computing. So that's our culture at NVIDIA. And let me share with you a few of the things we're going to talk about in this special address. First, digital biology. COVID-19 has thrust digital biology into a new light. And this year has been the DL moment for digital biology. AI flops. HPL in the top 500 list continues, but there's a new list, HPL AI. And in fact, look at every new system that's been announced or has gone operational in the last year. AI flops is the new standard by which supercomputers are measured. And in part, as we said, because of natural language programming, processing, NLP, impossible to do without a supercomputer. Another new technology that isn't brand new, but you've heard talked a lot more in the last year, is quantum. We'll talk about NVIDIA's contributions to quantum. And finally, ARM. ARM's been in the news a lot, but it's ARM's partners that have made so much progress for the HPC community. So we'll talk about what some of the ARM partners have done in the HPC space. Industrial HPC is a tipping point. Back in 2006, when we launched CUDA, molecular dynamics was one of the first applications that was GPU accelerated. The National Supercomputing Center in the US at the University of Illinois was one of the first to run NAMD on GPUs. And 15 years ago, a large state-of-the-art simulation on NAMD was about 1 million atoms being simulated for maybe 20 nanoseconds. Fast forward to today in the Summit supercomputer, and we see models 1 billion atoms being simulated for 500 nanoseconds or more. Even so, that isn't enough to make real breakthroughs, design new vaccines, design new drugs. And we see people looking to have 4-fold increase in what they can do in digital biology. At the same time, we've seen an exponential growth in AI models. Natural language processing, a poster child for AI and HPC, started out in 2017 with models like the Transformer. 65 million parameters at the time seemed huge. But look at today's state-of-the-art models, be it GPT-3 from OpenAI, 175 billion parameters. NVIDIA's Megatron and advances such as Universities of Florida Gatortron, based on the Megatron model, are making. And in fact, in the last few weeks, we've seen the first NLP models published with over 1 trillion parameters. And this isn't stopping. We expect by 2023, researchers will need to model models with over 100 trillion parameters. While this may seem far-fetched, think of the human brain. The human brain has roughly 140 trillion synapses. While a synapse doesn't equate exactly with a parameter in an AI model, it's a good approximation. Finally, back to molecular dynamics. Look at what's being done today by combining GPUs plus AI. US DOE researchers using the Summit supercomputer modeled COVID-19 with DeepDrive MD. They were able to run a 305 million atom parameter for a number of milliseconds. This represents a 10 million-fold increase in processing power from that 2006 era NAMD model. 10 million times the processing growth of atoms per second being simulated with a combination of GPU plus AI. And that's just the start. We see industrial HPC delivering transformational breakthroughs across industries. An example after example. GE Aerospace has worked with Oak Ridge National Labs to do large eddy simulations, simulating jet engine operations, leading to more efficient jet engines. In drug discovery, the US is of course not alone. We've seen the entire world double down on digital biology in COVID-19 simulations. In France, GENCI developed a code called TinkerHP. And TinkerHP was ported to GPUs for increases in performance. Today, TinkerHP is available on the NVIDIA NGC Software Hub. We're helping democratize high-performance computing in AI and taking work that GENCI does and making it available to the world. And of course, France has observed this as well. Qubit, a French pharmaceutical company, has taken TinkerMD and is working with 6 different pharmaceutical companies to advance drug discovery using the TinkerMD code. This continues in industry after industry. For instance, automotive. We know that automotive robots are simulated often before the software is put out into the factory. But BMW has gone far beyond that. With Omniverse, BMW is working to simulate the entire factory. Not only the robots, how cars move through the factory, and how the humans operate inside the factory, leading them to design more efficient cars in the factory of the future. In weather simulation, the weather company is now using AI to accelerate high-resolution weather forecasts to bring more accurate weather. You can now tell not just is it going to rain in your country or your part of the world, but is it going to rain in your city? And what is the temperature going to be? More accurately than ever. And finally, tech manufacturing, another area where we see AI and HPC coming together. There's a new class of algorithms, physics-inspired neural networks, that are addressing adding AI to the front end of CFD simulations to do things that simply weren't possible before AI with brute force computing. Let's go ahead and take a look on what's possible. This is a demo of NVIDIA's SimNet. Let's go ahead and roll that tape.
What we're showing here is an application of SimNet, which is a framework for running physics-informed neural networks on GPUs. As an example, let's take a look at how you can use SimNet to optimize the design of a heatsink. This involves solving a coupled fluid flow and heat transport problem. We've got a heat source in this chip on the board here, and a heatsink design on top of it that we want to evaluate over a number of different conditions in the chip. What we're going to do is search over a variety of different configurations of this heatsink. In this case, we've taken 2 of the parameters at the fin height. The center and outer fin heights are varied over a number of different conditions. We've also taken the volume of fluid in the metal, along with all of the materials that are in the heatsink and the surrounding air, and modeled them as a point cloud of about 3.3 million points. We then train a neural network on all those points using the various physical parameters, and map those onto a loss function governed by the partial differential equations of Navier-Stokes fluid flow and heat transport. The training takes about 4 days on a single DGX-1. Once the training is complete, we can evaluate and explore 25,000 different various configurations in a matter of seconds. Here we are visualizing a subset of those. You can see the heights of the center versus the edge fins are changing as I move these sliders, with the temperature map and flow instantly reflecting those changes. What we're looking for in this optimization problem is a condition where we've got minimum temperature for Tmax while still remaining underneath this gray plane here, which is the maximum pressure drop that our cooling system can provide. What we ended up finding was that the optimal configuration was not a completely rectangular block, but rather a roof structure. This makes sense because the heat is actually generated here in the middle, at the top of the chip. If you look at any other configuration, either the temperature or the pressure drops will increase. And finally, we are showing a simulation of transient flow with colored smoke vectors. The green vectors are showing flow that is slow, and the blue and purple vectors indicate faster flow. You can see here that there is slow flow through the core of the heatsink, but then there is very fast flow that comes over the top, which helps pull the heat from the center as it rejoins the streamlines on the other side. We can also turn off and on different layers of the simulation to literally see what happens when we change parameters, like the height of the fins or the pressure drop threshold. Note here that some combinations of parameters show what seems to be cool temperatures internally, but result in large drop in pressure on the backside of the heatsink. Using SimNet, we can see the effects of each change in real time, allowing us to quickly find a design that produces optimal cooling with acceptable pressure drops. Then we can quickly get that design into manufacturing, confident that it will perform as expected, the first time. These tools are something that we're using internally at NVIDIA to help model our heatsinks and do design space optimization. We expect to have a paper describing the core of the physics-informed neural network technology out soon.
Well, I'm sure after that SimNet video, everyone's going to want to run out and open up their DGX A100, take a closer look at their heatsink. Please don't do so while the system's plugged in and operational. Work with your sysadmin on that. Anyhow, let's go on and talk about Omniverse. Omniverse is NVIDIA's platform for connecting 3D worlds. It can accelerate scientific computing discoveries. Here's a little bit about how Omniverse works. Omniverse has connectors to dozens of different 3D data sources. All of the typical 3D design tools that you might use in design and manufacturing and others, as well as HPC design sources. With our ParaView Omniverse connector, you can connect directly to in-situ data from HPC simulations. Because everything is physically modeled, it gives you a lifelike realistic view, which is of course displayed beautifully with NVIDIA graphics and NVIDIA GPUs. But furthermore, because it's physically based, Omniverse can be connected into simulators. It can be used it can be used to build a digital twin, whether that digital twin is of a manufacturing plant or of the entire planet. It's physically accurate and can be used in collaboration. Let's take a look now at what a digital twin of the Earth might look like.
High-resolution weather simulations, as provided by DKRZ's ICON code, and vast amounts of observational data, allows us to determine the state of the Earth with unprecedented fidelity. But exploring and working with this data can be a challenge. Technologies like the NVIDIA Omniverse ParaView connector allows scientists to interactively analyze weather and climate data in 3D, to combine information from multiple sources, and to explore what-if scenarios. This takes us ever closer to a realistic, interactive digital twin of the Earth. Let's look at two examples. In August 2019, Hurricane Dorian developed into a massive Category 5 hurricane, causing over $5 billion in damage in the Bahamas and the southeastern U.S., with sustained winds of 185 miles per hour. Viewing high-resolution simulations like these integrated forecasting system simulations in Omniverse allows scientists to analyze the behavior of storms such as this in detail, interactively, and in full 3D. This not only aids in understanding the physics of weather systems, but also allows inaccuracies in models to be identified and refined. With the Omniverse ParaView connector, visualization modalities of ParaView, like streamlines, become available within Omniverse, and can leverage the RTX renderer or be fused with data from other sources. These sources can be static, or computed on demand, such as mapping service, surrogate model, or an AI-informed physical model. Here we show AI-based image segmentation of satellite data, which was used to detect flooded areas and to classify land use before and after Dorian hit. The network performing the segmentation can run as a service and be triggered on demand. Once we have interactive access to all this Earth science data, a next step is to play through different scenarios. On-demand evaluation of surrogate models or access to real-time physics engines can help exploring the impact of our actions in this virtual world. With access to real-time physics models as enabled by Omniverse, we can not only explore pre-computed data, but also simulate on the fly. Here, we use real-time fluid dynamics simulation to show the vapor plume emerging from a cooling tower. A user can quickly explore the impact of the plume, depending on the wind conditions or the steam output. Similar models can be used to interactively explore the dispersion of aerosols or contaminants. NVIDIA Omniverse is a powerful platform for massive-scale digital twin simulation. We're excited to see where it takes us next.
I know many of our Supercomputer Center customers have downloaded and are working with the early access version of Omniverse today. And again, I'm excited too as we start to be able to travel again. And I visit some of you in person to see some of your results. But as we all worked from home over the last year, it's been amazing to see the next wave of supercomputers going into production and being announced. NVIDIA's newest supercomputer, Cambridge-1. We built our first cloud-native supercomputer in the UK, thousands of miles away from our headquarters, as we were locked down during the pandemic. Cambridge-1 is now live, and we're working with our partners in the healthcare space to do some amazing work in the UK. You'll see Cambridge-1 on the top 500 list and more to come on that system. Last week, Tesla Automotive announced their new industrial AI supercomputer, about 6,000 A100 GPUs in NVIDIA InfiniBand networking. Tesla is, of course, well known for their self-driving car software. And even with the largest fleet of self-driving cars in the world, Tesla still needs to simulate, to run massive AI simulations in order to continue to improve their software and reach their goal of full self-driving. They've put a stake in the ground with this system. And I think this is going to be a bar than any other automotive company that wants to build a full self-driving system will need to compete against. A few miles away, also in California, NERSC installed the Perlmutter system, AI for scientific discovery. Perlmutter is now the fastest AI supercomputer in the world, over 6,000 NVIDIA A100 GPUs. It's a Cray HPE system, and we're really excited as it goes into production about the work that'll be done. We've also seen a new class of supercomputers based on our DGX SuperPod architecture. Recursion Pharmaceutical, a big pharma company that was just a startup a year ago. Many of you may not have heard of. And they wanted to get a supercomputer up and running as quickly as possible at their headquarters in Salt Lake City. They took just a few weeks to install the DGX SuperPod there, a digital twin of other DGX SuperPods around the world. We now have 13 DGX SuperPods on the top 500 list. But of course, supercomputing isn't just for on-prem anymore. We've seen a number of the major CSPs cloud service providers launch supercomputers. Microsoft Azure alone has not one, but 4 new supercomputers on the top 500 list. In fact, in the top 30 list, number 26 through 30. Located around the world, you can now rent a top 30 supercomputer in the cloud directly from Azure. Once again, this system is based on the DGX SuperPOD reference architecture, uses NVIDIA's A100 GPU, and NVIDIA InfiniBand networking. 2 systems in Europe that have been announced in the last year that we're extremely proud about. First is the Leonardo supercomputer at Chenica. At 10 AI exaflops, it'll be an amazing system for AI and HPC giant scale problems. And the world moves ahead. Not long after Leonardo was announced, CSCS in Switzerland announced ALPS. ALPS will double Leonardo's performance using our next generation Grace ARM-based CPU, and it will deliver 20 exaflops of AI performance. It'll be one of the most capable HPC systems, equally capable in AI. The top 500 list was released just a few hours ago. In fact, just an hour ago. I'm sure many of you have already studied that list, and great to see all of the NVIDIA systems on both the top 500 and the green 500, delivering energy efficiency to the world's fastest supercomputers. Superclouds, cloud-native supercomputers. These aren't just the systems in Azure or in AWS, but on-prem systems every day need to have the same attributes that you expect from the cloud. A supercomputer today can't just be locked up in the back room and made available on a private network for 10 or 15 researchers. The investment required for state-of-the-art AI supercomputers means they need to be shared, and they often need to be shared across organizations. A supercloud can be made secure with NVIDIA's BlueField DPU. Our DPU provides multi-tenant bare metal performance while still providing the security you expect of a cloud-native system. Only a few miles from our own Cambridge 1 supercomputer, we saw the University of Cambridge deploy a system on the top 500 list using NVIDIA's BlueField 2 DPU. The Cambridge system was built by Dell using our own HGX 4 GPU platform. I'm very excited to see that system with its very high ranking on the Green 500 list. So congratulations to Dell and to University of Cambridge for that system. Of course, DGX A100 is a great platform, but we don't keep it to ourselves. It's a reference architecture that, as we said, is shared with all of our OEMs and all of our cloud service providers. You know, at ISC, we always like to make a few new announcements. And this year, we're expanding HGX beyond the traditional HGX 8 in 4-way NVLink-based platforms and introducing HGX with our PCIe-based GPUs. It's a perfect platform for building a system with your OEM or for using a system that your cloud service provider has offered. When you use the HGX platform, you're guaranteed that all 2,000 of the NVIDIA GPU accelerated applications, those that are on our NGC Software Hub, and many others available from leading software providers around the world, will run to NVIDIA certified standards. So of course, it's going to include our NVIDIA GPUs, includes new performance technologies in the storage space, such as Magnum IO, and of course, to make that DPU usable is Doka. Doka is quickly becoming to the DPU what CUDA was to the GPU. So we're super excited about all the new HGX AI-based platforms that our OEM partners are announcing this week at the show. Powering many of them will be this new GPU, the NVIDIA A100 PCIe 80GB GPU, the world's highest performing PCIe-based GPU. Now, many of you are familiar with the A100 80GB from our earlier HGX 4 and 8 GPU platforms. This is the same A100 80GB GPU fit in a PCIe form factor for the broadest range of servers possible. And we have every leading OEM lined up in supporting this new PCIe GPU. And it has all the same features that the earlier A100 systems had. So I'm not going to talk about all of those, but one of those I do want to highlight is the multi-instance GPU, or MIG. MIG was new in the A100 architecture. I think a lot of people aren't focused on it yet. When you build a supercomputer, you're thinking about putting multiple GPUs together in a server, and then even connecting hundreds or thousands of servers together. So you don't think about a fraction of a GPU. But again, many times across a general purpose center, people run large codes, but you also have a wide variety of users on. Some may just be doing development, some may use smaller codes, and of course, with the adoption of AI across the HPC landscape, as those AI-enhanced HPC applications get deployed, you have more and more of a need for inference. And these are all areas where MIG can help. MIG takes the GPU and lets an A100 look to the operating system like up to 7 GPU instances. So a single PCIe server with one A100 can appear to serve 7 different users, each under the impression or looking like they have a GPU with a fraction of the performance. And again, you don't have to decide ahead of time, do I need a small GPU or a big GPU? MIG can be dynamically configured in your system. So one of the great features, I'm really looking forward to more adoption of the A100 in both the PCIe as well as our other HGX form factors. Now on to some of the other exciting announcements in the networking space. We're excited at the show to be announcing the details on our NDR 400 gig InfiniBand systems. Of course, 400 gig gives you twice the bandwidth of 200 gig HDR, but it's a lot more than that. Look at these results that we've achieved on early NDR systems, improving natural language processing, deep learning recommender systems, and computational fluid dynamics, codes that need to run on every AI supercomputer. And of course, because power is important, NDR delivers 60% lower power performance for your supercomputer. That translates directly into more power available to run your applications. One of the real areas where we've seen improvement in NDR is in AI acceleration. We're moving certain types of AI acceleration into the network. Sharp accelerates AI primitives in the network switch, and NDR switches provide 32x the Sharp acceleration that has made the current HGX or HDR-based InfiniBand systems so popular. And look at the performance on a petabit per second base, 1.6 petabits. A new petabit being the new reference by which we need to judge switches. So we're super excited, and we expect on the top 500 list in the fall, we'll see the first NDR deployments. Like the current family of HDR and earlier switches, NDR comes in all sorts of sizes and shapes, from the smallest top-of-rack switch with 64 NDR ports, all the way to a new record-setting 2048 NDR ports in our largest switch. Now, one of the hallmarks of InfiniBand is not only being leading edge in performance, but being backward compatible. We know that many of you don't have the luxury of replacing your entire data center when you buy a new system. You need your new supercomputer to be backward compatible with your old supercomputer, so you can mix and match networking. So of course, NDR is now also supporting NDR 200. So you can take that new switch and double the number of ports. And beyond that, it's compatible with all the earlier generations of InfiniBand as well. So it can plug and play with earlier existing InfiniBand switches and InfiniBand servers. Super excited again about the advances NDR is going to bring. Across the industry, and this is something industry is learning in a trend that started in supercomputing. Supercomputer was always about the data center. You bought one supercomputer and it was in your data center. But as systems become more and more complicated, data center is becoming the new unit of compute. Customers want to buy a data center at a time. And they're going to put different types of architectures in that data center. Of course, scale out is a classic HPC design. And technologies like Magnum IO will accelerate the storage for scale out and the increasing traffic in east-west traffic in your data center. Virtualization is still important for the enterprise, and with new GPU support by all the leading hypervisors, we see scale-up computing continuing, stacking up multiple VMs. With VMware and NVIDIA AI Enterprise software on top of NVIDIA certified PCIe-based servers is the perfect platform to run small and medium scale AI and HPC workloads. And finally, new applications are designed as a series of microservices. Those microservices may run on a hypervisor-based system or natively in a GPU container. So NVIDIA is building reference architectures for all of these with GPUs and NVIDIA networking optimized for each of the three styles of computing. GPU direct storage. GPU direct RDMA has been known for many years in the InfiniBand space, and we're extending it with GPU direct storage. It's the same idea, except applied to storage. Take the data directly from storage, either on a locally attached direct storage or on storage that's attached via the network, and create that data path flowing direct from the PCIe switch to the GPU. This, of course, requires collaboration across the ecosystem with the GPU, the network, the storage provider, and the file system provider. We're working with all the leading HPC storage companies listed here. Quantum. There's billions of dollars of new funding pouring into quantum. And you perhaps wonder, what does NVIDIA have to do with quantum computing? Well, first of all, specialists agree. The future is not just quantum computing, but hybrid quantum classical systems. And we expect when quantum systems reach industrial types of tipping points, they'll be used in hybrid systems with GPU accelerated systems as well. But meanwhile, a challenge remains. To build useful quantum computers, the world needs to do quantum simulation, and it simply takes too long. A quantum state vector simulation can take 10 days today on a 2-socket server. With the new cuQuantum SDK, we accelerate that from 10 days to 2 hours. And that's for tens of qubits. To build a meaningful system, experts agree you'll need on the order of thousands of qubits. And in fact, doing a tensor state simulation with thousands of qubits would take about 9 years. We can't wait 9 years just to do quantum circuit simulation if we want to see quantum adoption. We've taken that 9 years down to 4 days on the DGX A100. So we're working today with all of the leading quantum labs in ensuring they have access to cuQuantum. So you'll be hearing a lot more about cuQuantum as we evolve that software over the coming months. Now on to our ARM partners. This is an area where we've seen tremendous growth of so many partners over the last year. And NVIDIA is further accelerating that with our ARM HPC Developer Kit. It'll be available this quarter and coming soon, featuring of course, an NVIDIA A100, NVIDIA's BlueField-2 DPU, and an ARM CPU from our partner Ampere Computing, the Ultra ARM CPU. NVIDIA Grace. This was our big announcement at GTC, and of course, the AlpSpace supercomputer launching in 2023 is one of the first systems that will use the Grace architecture. Grace solves the GPU to CPU memory bottleneck, increasing by orders of magnitude the performance of accessing that CPU memory and giving you a cache-coherent memory space between the GPU and the CPU. It'll use our 4th generation NVLink technology, connecting not just the GPUs, but NVLink all the way out to the Grace CPU. This is designed for giant scale HPC and AI applications. And you can see some of the performance improvements that we're simulating today as we continue to simulate the Grace chip coming in 2023. So as we've talked about, the HPC community needs to address a diversity of problems, and that requires architectural flexibility. One size does not fit all in an HPC data center. And ARM and our ARM partners enable that architectural innovation. If you look across the landscape of existing and announced ARM architectures, many countries, CDAC in India, ITRI in Korea, Ampere Computing in the US, SI Pearl representing the work of the European Processor Initiative and the processor design for next generation European supercomputers, Amazon Graviton in the cloud, and of course NVIDIA Grace. You'll see different types of architectural innovation across all of these partners and all of these processors. Creating a computing ecosystem is hard. We've worked for 15 years to create the NVIDIA ecosystem on top of x86. And of course, that still represents the majority of the servers being shipped. And we love x86 as a partner, and we'll support x86 CPUs for forever. However, I think there's a lot of room for architectural innovation, and I'm really looking forward to that ARM number growing with all the architectural innovation going into ARM. We've got a great ecosystem, lots of developers, over 150 SDKs, adoption by all the major OEMs and CSPs, and really looking forward to the next year in high-performance computing. And I can't wait to, everything willing, be back in Frankfurt in person next year for ISC 22. So there you have it. We've reached a tipping point for industrial HPC. Digital biology, it's been the DL moment. We've seen the rise of cloud-native supercomputing, expanding ARM ecosystem, and of course, our latest PCIe-based A100 and NDR-based InfiniBand launching here at the show. So with that, we'll go right into our Q&A panel. We've got a panel of experts here, and they're all live. No takes here on the Q&A. And so let's go ahead and start with the first question. How accurate are AI simulations in comparison to traditional simulations? Let's see, Geetika, Why don't you take the lead on that?
Okay, thanks, Mark, for the question. And thanks, audience, for this is a great question. I think this comes up often. How accurate the AI models are for a HPC use case. So I would want to when I answer, I would like to step back and remind that simulation application is also an approximation, where it is trying to use the laws of physics to approximate and predict what the behavior of the material or the particle uh, would be. But over time, that simulation application has become more and more mature, and definitely, the results have a higher trust factor. Now, with the advent of AI, you have to see that the AI model is getting trained using the data coming out of the simulation. So, yes, initially, the AI model may not be that accurate, but what the researchers are doing is they run the simulation and the AI model in a tight integration. So wherever the AI model is weak, they use the simulation to create more data set or more training data set, and that is used to train the model. And over time, this process is called active learning. And over time, the AI model becomes as accurate as a simulation. It's almost like an analogy of a professor and a student. Initially, the professor is teaching the student, and as the student gets more and more practice, the student and the professor, they actually work as peers and they can give feedback to each other. And that's what ends up happening. As the AI model gets more and more accurate, it is actually then able to inform what simulations to run in the future, and they can work in a tandem. So that's the process where how people are making the AI models more and more accurate. And yes, when they start, they may not be that accurate, but over time they do get accurate, and we are seeing that trend.
That was a great answer, Geetika. And the only thing I think I'll add is people will continue to use traditional physics-based simulations when they need to. But when they don't need to, they'll accelerate them with AI, with data science-based applications. And if you think about it, the output of simulations, as you said, are not always 100% correct, right? That's why when a COVID vaccine candidate is generated by a simulation, it's then first tested out in the lab, right? And then after it's tested out into the lab, then it starts going into human trials. And so again, if we had waited for 100% accurate physical simulation, we probably would not have seen yet the first COVID vaccines, or certainly have seen fewer of them. So again, it's amazing to see the progress there. Next question. How does the performance of GPU applications stack up on ARM versus x86? Tim, you're working with a lot of our ARM software. Why don't you take a first pass at that? We'll see who else might want to jump in.
Sure. Well, I mean, the simple answer is that we're seeing great performance on ARM-based systems as compared to x86. And we take a look at that both from the perspective of GPU accelerated applications and applications that aren't GPU accelerated, and we see just tremendous performance. I think a lot of that has to do with the maturity of the software stack and tools, both from ARM as well as from NVIDIA, and it's looking very, very good.
So I think that ARM and x86 are both great CPU architectures, right? And what NVIDIA focuses on is really accelerating the performance on the GPU, but also on accelerating at the data center level, right? It's not about any individual processor, but it's about looking at things at that full stack. When we build our DGX SuperPod, right, our largest DGX SuperPod we have in-house, Selene, on the top 500 list, has over 4,000 GPUs. But it's not just about the GPUs. It's about accelerating the entire performance. And in fact, I'll let everyone do the math. You can go look at other systems of different numbers of GPUs on the top 500 list and look at the ratio of the performance. And then look at MLPerf or look at other applications, right? The CPU adds value, the GPU adds value, the network adds value, the software adds value, but being able to integrate and optimize across that full stack is really, I think, where NVIDIA's value comes through.
And one quick point I'll add there, Mark, and this probably gives credit to a lot of the work that Tim and his team does. When we work with developers on porting and working on ARM specific applications, the experience that we saw time and time again was that they got that performance with very minimal effort. So I think initially, as we started thinking as a porting exercise of moving from x86 to ARM, but using, I think, a lot of the tools that Tim and team has built around the HPC SDK, as well as just the ARM ecosystem as a whole has built in terms of allowing that port to happen very seamlessly and to get that performance almost out of the box. I think it's been sort of a nice surprise for a lot of the folks who've been engaging with the applications and porting from ARM to x86.
And that will continue to let our customers decide. Who has the best innovation for them, right? There's of course different choices in x86 processors, and you'll see many different choices of ARM processors, as you already do today. And I think customers will often pick the ones that have the right level of innovation and deliver the right value for them in their application. And that might be different at the edge, in the data center, in an industrial data center, and out in a cloud use case. Next question. So in the heatsink example, how exactly is this different from random or guided search algorithms used in optimization problems? This was described almost exactly as a differential equation. Geetika, do you want to take that?
Yes, I can take that. So yes, SimNet is doing the design space exploration, just like what you described in the question. But the point of SimNet is that it is able to do a exploration of much more permutation and combinations within the same time, or even in less time. I think it's about how SimNet does it and how it makes it easier for the users to explore a lot more variables, a lot more geometries, and still be physics informed, and do it in a matter of seconds or minutes or hours versus days and weeks.
Great. Next question. What are the programming models supported by the HPC SDK for the ARM HPC Dev Kit? Well, Tim, that's one right up your alley.
All right. It's a great question, and with an easy, crisp answer, all of them. So the HPC SDK, has had full support for ARM server for well over a year. In fact, its first release in May of 2020. ARM was treated as a platform of equal importance to x86 and Power. And so from automatic acceleration of ISO standard languages with C++ and Fortran to incremental optimization with directive-based programming, whether you choose OpenACC or OpenMP target offload, and of course support for programming in CUDA to directly target the GPU and get great performance when hosted by an ARM server. All of those programming models are fully supported on the ARM HPC Dev Kit in the HPC SDK.
Great, thanks, Tim. Next question. What is the availability of NDR InfiniBand? Gilad, we'll let you take that.
Appreciate that, Mark. So we definitely were excited to announce the NDR switch systems today, I believe. And we will start to sample out and send NDR switches to our partners and customers in a couple of months from now. So it's pretty much going out. That will deliver not just great benefits on the networking side, meaning going to the 400 gigabit per second and bigger switch radix, so you can connect more nodes with less switches and save power and save real estate. But we're also bringing new in-network computing engines. Meaning, if you look at a network for supercomputing, it's not just speeds and feeds anymore, right? It's how you move compute to where the data is. how you can improve the performance of applications by bringing compute everywhere. And by bringing the in-network computing engines such as Sharp and the new engines as part of NDR, we're able to analyze more data and doing more arithmetics on the data as it moves within the data center. And you presented some of the advantages of that on improving scientific or CFD applications, NLPs, and recommendation models, and so forth. So short answer, a couple of months, we start shipping the NDR devices, and we'll be in a full production or general availability by the end of the year.
Thanks, Gilad. And you know, I know our internal architects are super excited about getting NDR. And of course, we're not going to just ship faster switches. We're going to optimize all of our designs, starting with our own DGX SuperPod. And again, we're still working on the different design trade-offs there, but that's one of the things that I expect at supercomputing. We'll be talking more about how NDR can help to optimize new DGX SuperPods and other OEM-based systems that follow that same reference architecture. Next question.
Great, and it's great. It's great that we bring in the full stack, right? So it's more than just the component perspective, not just the network, not just the GPU, not just the CPU, but actually bring the full SDK, the full software stack, and can optimize everything from the applications all the way to the drivers underneath.
You know, I know before the Mellanox acquisition, we worked very closely with you, right? But there's nothing like having all of those Mellanox engineers in the same virtual room, in the same virtual building, and you know, every single piece of NVIDIA software, every piece of NVIDIA hardware, every engineer is thinking about how do we take advantage of these new features. So it's very exciting times. Can you talk about how DPUs play an increasingly prevalent role in HPC AI architectures? I know who I'm going to hand that one off to, but you know, I know a lot of our customers are thinking about that. We had last week we had our internal technical training for HPC, and usually for ISC. Normally we just have internal speakers for it, and last week. I was very privileged to have asked Paul Collegia of University of Cambridge, because he's deployed one of the first top 500 supercomputers with DPUs, and he came in and talked about just this. But he's not on the Q&A panel, but Gilad, I know you work a lot with Paul at University of Cambridge, so I'll let you take this question.
Thanks, Mark. And we did have a session at ISC together with Paul, and actually talking about cloud-native supercomputing and so forth. So if we look on HPC, we can definitely see that HPC is going everywhere, right? AI is going everywhere. HPC serves more applications, more users, and this is where you need to start bringing more multi-tenancy support into the supercomputers that we build. More security, right? We want to work with more industry applications. You want to work with medical companies. You need to secure the data. So if you look on that, one of the most complicated workload right now on a supercomputer or a data center, it's actually the data center operating system. It's actually the data center infrastructure workloads. That's become one of the most complex workloads, and it takes a great toll on the CPU performance. And when we build supercomputing, it's all about performance, right? We need the massive compute power in order to actually solve the problems that we want to solve. So this is where we kind of stuck. How do we keep bare metal performance and bringing multi-tenancy and isolations, all the infrastructure management that we want? This is where the DPU comes to the rescue, right? The DPU, it's a full data center on a chip. It is being built to run the infrastructure management and not just offload the infrastructure management from the CPU, but also to accelerate that with engines around securities, file system, and so forth. So moving forward, every supercomputer will have a DPU. Every supercomputer will have a DPU in every server to run the network, to run the infrastructure operating system, maintain bare metal performance on one side and multi-tenancy support on the other side. And one quick note, it's not just there, because if you look on the world of scientific computing, we're starting to go all the way to the edge. Do the first analysis at the edge and then send the data after the first analysis to the main system. The DPU, being a full data center on a chip, it's a great component to be an edge component. Edge device component is multiple DPUs, for example, with GPUs. That's where we're going to see the edge computing being started to be.
Hey, Gilad, that's a great point of DPU at the edge. But you brought up healthcare, and so we don't have time for any more questions. But go a little bit, just 1 minute over here. Nicola, I'm going to put you on the spot. You work with a lot of our healthcare customers, and you know, privacy of healthcare data is certainly paramount. How do you see the DPU helping out in the healthcare use case, where we go all the way from edge instruments to, of course, supercomputers?
We can't know for sure yet, but I expect to have it a major influence. So privacy is a major component for medical applications. It's not that we handle with random data. This data is genomic data. This is patient data. This data should not be leaked. It really has to remain secure. So DPU can really accelerate the process there for the secure compute there. But I also see a lot of applications in terms of big data centers or supercomputers. So I don't expect, for example, that every hospital probably will have their own supercomputer. But there's a reason why we do have a healthcare team specializing on this application, because it was also mentioned in the discussion before, it takes more than just put compute somewhere to actually solve a problem. To really tackle an application, it has to have the combination of the algorithms that come from the researchers, the infrastructure, as well as the compute. So if you consider, for example, the genomic world, if you have every single one of us has a billion of information in their DNA, and to make actually inside of this information, it takes a lot of compute to actually compute that. And it's a combination of getting this information by a sequencer, accelerating this process, getting this information in the storage, getting this information from the storage to the compute, and vice versa, to actually make insights of that.
Well, thank you. And, thank you very much to all of the panel. I get to work with you every day and can ask you questions every day. I'm sure our audience wishes we had another hour that we could ask more questions, but I'm sure there were some questions that we didn't get to. We'll follow up with anyone that asked a question. And by the end of the week, we'll have the video and the slides posted on the NVIDIA Download Center. So have a great virtual ISC. Participate in the sessions, come to the NVIDIA booth, and you can ask more questions there. And again, until we're able to meet in person, thank you all for coming and have a great week.
Thank you, Mark. That was great. Fantastic presentation and great discussion with the panel. Lots of exciting news, lots of announcements, and we look forward to having further conversations with you. We're ready with our teams to have the in-depth discussions and to go even deeper in what we bring to market. I wish you all a great ISC 21, and hopefully we get to see some of you face-to-face either at SC 21 or next year in Frankfurt at ISC 22. Thank you so much. Bye-bye.